All right, guys, I'm back with another subtopic here. In the last video, we discussed some feature engineering techniques, and we combined all those data into one data frame, right? So in this video, what we will do is, after taking 133 features, we will apply some dimensionality reduction techniques using TSNE. In short, we can also say TSNE. So here data is very large. We have around 8,78,000 data values. So applying TSNE to this data set can be quite cumbersome. Instead, what we will do, we will take 1% of this data and we will try to apply TSNE on that. So this function is helpful to divide the data. Here I'm passing my data frame and the target column. So we have to take the features separately and the targets separately. And then for dividing, we can use a train test split function, which is a part of sklearn. This function takes xy and the test size. Remember, we are taking x train and y train. So that would be 0.1%. Since I'm specifying test size here, this takes the percentage here, 0.9, and that would be saved in X test and Y test. So we are not returning that. Now here I'm using stratify equals to Y. This ensures that the target distribution in our train and Y train and X train is very much similar to the original data set of target distribution. So stratification is a special sampling technique that we are using here. And apart from that, I'm using random set equals 42. This randomizes data sufficiently, and at last we are returning x and y. So this is used to divide the data. And the next function is about plotting the TSNE figure, TSNE plot. So here we have 133 features. So by not considering the whole features, what I will be doing is to consider only the 20 best features that actually contribute to the uh, target column. So this function, it has these many parameters, x, y, k, and perplexity. So these two have default values. To select the best 20 features, there's some class or method or technique such as select k-best, which is again a part of sklearn. So this will apply some statistical techniques in the background, like chi-square testing or other similar testing approach, which are suitable for categorical data. So here it takes k value, which is 20, and this is the object of that. Now we need to fit our x and y once you get the object. And then we have to transform our original features, that is 133 features. And this ensures that we will end up having 20 best features. And after this, I'm doing the standard scalar approach, basically column standardization, and applying TSNE with n components equals 2. So from 133, we are getting 20 features here, and from 20, we are again dividing into 2 features. So TSNE ensures that it happens correctly, and perplexity is 50, random set 0. So once you get the object of TSNE, we can again fit our data on that with the help of that object. And finally, we get the projections, which has the two-dimensional features. So once we have this, we can easily plot the scatter plot. So this is a scatter plot function, and this is the layout of the plot, basically a custom layout, and then finally showing the plot. So this function is basically for plotting the t-skew. So now let's see uh, by actually using these functions. So in this case, I'm using this function here, which returns x10 and y10. So here I'm getting x10 and y10 by dividing the data and in the form of by using stratification split, and we will have 1%, 10% of the data, and then we have to take we have to plot our t-SNE. So when k is 20, by default it is 20 only here. So when k is 20, we can simply use the plot t-SNE function by passing our x10 and y10. So here I'm getting this print statement. Basically, it's because of this code. This is to show the features when we get after applying select k-best. So you can see here we have 20 features. And this is the 10% of the data. 0 point is nothing but 10%. So 10 by 100. So 87,804. These many values we have. And the t-SNE plot is like this. Here we can see the clusters on the whole 39 classes. And we know it's not a good spread. It's mainly because we are using 10% of the data, and we are using only 10%. If we had used whole data, maybe we would have found some other insights, but that's fine. That's fine. And moreover, this class data, this target variable is not balanced, and even that can be the issue. So yeah, these are the observations which I have written. And let's not take 39 classes. Let's only take 12 top classes. So to get 12 crimes, we can use another function, which basically takes the top 12 crimes by using the value counts and then extracting the top 12 using the list indexing method. So we'll have the top n crimes names, and using this we can do some filtering techniques to select the data which is true for this condition. For I in top n, which is nothing but the crimes, for each crime, doing some filtration techniques, we can easily append the data in this list, and then we can concatenate everything using pandas concat method. Now, since there won't there won't be any randomization, we can use randomize technique to randomize the data, and that's how we can return the final DF. So to get the top 12 crimes, we can use this method function, and here I'm using it. So once we get this data, we can again divide the data using divide stratification function. So we will have x10 and y10 from the 10% of this variable data. So again, plotting the t-SNE. So we are having 78,000 values and 20 features, and this is a spread for the top 12 crimes. This is far better than this plot. Here we can see the clusters forming very clearly than the previous plot, but still there is some overlap, and moreover you are still using only the top 10% of the data, right? That can be the issue here, but overall the spread is quite better compared to the previous one. Similarly, apart from taking top 12 crimes, we can take a top 5 crimes. So same function I'm repeating with only by passing only n equals 5 there. Previously, we passed n equals 12, which is the default value. So in this case, I'm passing n as a 5, and again doing the stratification split, getting the x and y trend. Using this, I'm plotting the t-SNE. So here I have 52,423 data values, 20 features. And this is the overall spread for the top n crimes, top 5 crimes, basically. Uh, of course, this forms perfect clusters, but there is some overlap between non-criminal activities and latency theft. So if you had observed my previous videos, I discussed about this density plot. So in this GIF, we actually saw the top crimes that actually appear in this first row. It's either latency theft or other offenses or non-criminal activities. So there is a overlap, clearly overlap between non-criminal and latency theft. So this is something that we can observe in this also, like orange color and green color have a huge overlap. So that's it for this video, and this ends the EDA part of our project. Now in the next video, we'll discuss some modeling techniques and feature engineering for the test data. All right then.